morning, everybody. I will try to explain in 20 minutes a pretty complex issue, and I hope I will clarify just the most important steps. The first question is Impol aluminum industry and why we are thinking about magnesium, or why we are doing something with magnesium oxide. For those who don't know, magnesium is alloying element in aluminum alloys, in wrought aluminum alloys. Means that I'm sure that you know that a lot of aluminum are in cars or in some in planes, aerospace vehicles. All those alloys consist of basically 30 alloying elements. I will talk about this afternoon. But one of these elements is magnesium. And magnesium is present roughly between 0.8 and 1.5%. Means that Impol annually needs more than 5,000 tons of primary magnesium. And the problem is that in Europe, nobody produces primary magnesium. You see, in Europe, we need around 150,000 tons of primary magnesium. And there are some small production in Norway or something like that. Means that we are interested in some projects considering 5,000 to 10,000 tons of primary magnesium, or production of 5,000 to 10,000 tons of primary magnesium annually. But the problem is that this primary magnesium, because in industry, at the end of the day, everything is cost. The cost is the most important property of material. So the primary magnesium should be competitive to Chinese one. And the cost of primary magnesium from China is roughly 3,500 euros per ton. It's expensive material. But when there are some political issues, cost could be also, Chinese will say, cost would be 15,000 euro per ton. And then we have problem. So this was the main reason why we try to, I will not go in details because time is very short. So we found in literature and during some conversation that this aluminothermic reduction of magnesium oxide could be the cheapest way. We know that some companies in the United States are doing primary magnesium in this way. And in principle, it's very simple reaction. You take magnesium oxide and aluminum as reducent, and then you get spinel, this complex oxide, and primary magnesium. It looks very simple, but the problem is that this reaction occurs at pretty high temperature, roughly around or above 1,400 degrees, mostly in vacuum. And usually they are using aluminum powder. Means that, of course, I put it here that aluminum is liquid, but it's liquid during the reaction. As a raw material, it's a fine powder. Fine powder is very expensive. Means that you have to press magnesium oxide and aluminum, and then you can get magnesium and spinel. But it will be more expensive than this primary from China, you know. Means that it will not be competitive. So we try to investigate here It's a lot of information, but so what we try to investigate is under what conditions is it possible to use suspension of magnesium oxide particles in aluminum melt, because this could be the cheapest way, as an input mixture for the continuous production, because when you are mixing two powders, press the pellets, then you are doing in a non-continuous way. You just put in furnace and make the aluminothermic reduction, and then you repeat the entire process. So we are looking for the continuous production, and of course we try to develop even on pilot scale. The first part we observed in laboratory. The second part was on a pilot scale. The continuous introduction of magnesium oxide particles into the aluminum melt, because this we recognized would be the most critical step in such a reduction. So I will try to explain very shortly our experimental work. So we used, of course, several magnesium oxide powders, all commercial, all made from seawater. Because maybe you don't know, but downstairs in seawater, there are 1,250 ppms of magnesium chloride. Means that ocean is the basic source of a huge amount of magnesium. And from magnesium chloride, it's easy to produce magnesium oxide. So we use these commercial powders. And of different average particle size. The first one was very fine with submicron particle size, and the last one was very coarse. Purity was very high, and then what we try to do, but in a pretty simple way, we try to observe the kinetics of this reaction, but not to make some kinetic studies, you know, it's too ambitious for us. But the main idea was, the question was if this kind of aluminothermic reduction, when we have magnesium oxide particles into molten aluminum, would be fast enough because only in that way we can then create continuous production. If it's not fast enough, then it will be impossible. So, okay, we prepared two mixtures, one of magnesium oxide and aluminum powder, and another one of 20 volume % of magnesium oxide particles in aluminum matrix in the form of ingots cast from a suspension of particles in aluminum melt. You will see later on. So, of course, we use this induction furnace in argon flow atmosphere. And here you will see also what we try to make in a pilot scale. We use, we call that dosing wire. The idea was to put magnesium oxide powder into the core of aluminum tube. We found also that this is a very good way of alloying some alloying elements in aluminum melt. And you will see here, we produce this wire, means that you have cladding of aluminum. And in the core, it is magnesium oxide. And what you see here is a vortex of molten aluminum, so you can introduce magnesium oxide particles directly to the vortex. Vortex is created by electromagnetic pump. This is a very convenient unit in aluminum industry. If you have melting furnace, then you have electromagnetic pump, and in the charge well of the electromagnetic pump, you have this vortex. And that's the best way for alloying. That's the best way for alloying. Okay, of course, a lot of questions about the geometry of the dosing wire, because, of course, our task was also to produce green primary magnesium, means that we should use also recycled aluminum, you know. I cannot go in that details because I would like to show you the kinetics. A lot of work, but in principle, we investigate two mixtures, as I said, at some different temperatures, between 1,400, 1,450 for different time, 10 minutes or 1 hour. And what we found is here. And this was one of the key results for us. We found that at 1,400 degrees, in 10 minutes, you can achieve very high yield, reaction yield. But, of course, only if you use magnesium oxide particles in submicron range. So, in 10 minutes, it's very fast and fast enough for continuous production. So, of course, kinetic is one thing, but also the equilibrium vapor pressure, which can be calculated from the thermodynamic data, is also very important, and we found that under this condition it will be around 1 bar, which is perfect. Means that we can use argon flow atmosphere for moving gaseous magnesium from a chemical reactor. What I would like to show you here is, because then I will explain you a little bit also the economy, is maybe this flow chart, because this is the basic idea of the some future plant for aluminothermic reduction, for continuous production of primary magnesium by aluminothermic reduction. You see here, this is electromagnetic pump and melting furnace, in which we are introducing those wire, this wire which I shown, and aluminum scrap, which is necessary to introduce for molten aluminum, to get the molten aluminum. And then in this unit, you get this suspension of magnesium oxide in molten aluminum, and then you can put this molten metal to the flow tube reactor. We said 20 minutes at 1,400 degrees. Under this condition, magnesium is gaseous, and with argon, you put magnesium gas into 2 stages heat exchanger, which is convenient unit. Also, if you are producing magnesium by electrolysis or by pigeon process, you should get this heat exchanger. And then of course, liquid magnesium in holding furnace, and then you can casting magnesium ingots. But where is here the economy? Because what I said are doing also Chinese, taking dolomite, put into the furnace with pigeon process and make magnesium. Where is here the economy? First, the economy is in continuous of this process. And then another economy is in spinel. 1 ton of spinel is 900 euros. So with the cost of spinel, when you sell spinel, you can cover the cost of aluminum scrap. Means that, in simple words, you have raw materials for your production basically free of charge. Because with the byproduct, with the spinel, you cover the cost of aluminum scrap. Means that this is the idea. What we made, as I said, and then I will show my conclusion. We made in pilot scale this first part. We developed this dose wire with the proper geometry. Proper geometry means that in 20 minutes at 1,400 degrees, you should achieve high yield. And at the end of year, you should produce 10,000 tons of primary magnesium and even double, around 20,000 tons of spinel. Other parts are under the consideration because to put this in reality, you need roughly 35 million euros for putting this into real life. But according to the high price of magnesium, the payback for this investment would be 3 years, which is perfect, 3 to 4 years. So the conclusion, okay, this is the description of some of those units. There is no time for that, but maybe based on experimental work and in the laboratory and on a semi-industrial scale, we have confirmed that it is possible to replace aluminum powder with aluminum melt. We found that at temperature above 1,400 degrees, we get almost complete chemical conversion. The reaction takes place at atmospheric pressure in atmosphere of flowing argon. It's very rapid. In 10-20 minutes, you can achieve high conversion of the reactants into products. Magnesium oxide is obtained from seawater. Aluminum melt from post-consumer scrap. Post-consumer scrap is scrap coming from end-of-life products with footprint almost zero or very low footprint. Means that under that conditions, the primary magnesium will be the green one, which is also a huge advantage. So, of course, doing everything with magnesium gas at 1,400 degrees, it's very dangerous, and that's one of the problems with that production. But this is the only way. This is the only way for such a production. So, and this was invention, gold invention, and here are my co-workers from Impol, a huge group of engineers. So thank you for your attention. If you have some questions.
Do we have questions from audience? Yes,
Okay.
please.
Oh.
And congratulations, it's impressive. What I would like to ask, you mentioned you went from laboratory through semi-industrial scale, pilot production.
Yeah.
What were challenges when you upscaled? Because usually in laboratory level everything works fine, but when you go into upscaling, there are some barriers, obstacles,
Yeah.
which we do not think about them in advance.
I said that we scaled up just the introduction of magnesium oxide particles into the molten aluminum. We did not run the production of primary magnesium, but what we run in laboratory scale. But in a pilot scale, we produce this dosing wire. And we developed the way of introducing this dosing wire into the vortex of molten aluminum, which is critical step. Because you can imagine, if you mix aluminum powder and magnesium oxide, then you have very good contact and you have a very homogeneous sample. So you have to do the same with magnesium oxide particles putting into a molten aluminum, which is critical. Also, the wetting angle could be critical point. So you have to put some magnesium also in molten aluminum to improve the wetting angle, etc., etc. Next steps will request huge investment. And this is why we are talking about invention, not about innovation. You know, that's at the end you need roughly 30 million euros, and this is of course very risky. But there are two projects. One will be in Romania, another one will be also in the first one will be financing by European Union, and another plant in Romania will be financing by US money. Means that this would be very interesting way for producing primary magnesium.
Yeah, I think we have one more question.
Yeah.
Or not? Did I see some?
Yes?
Yeah, yeah.
So magnesium oxide we get from the sea, and what about aluminium powder?
Aluminium powder is from aluminum. We used in this work we used commercial aluminum powder. As I said, it's very expensive material. But basically, you can produce this in something like spin melter or something like that, you know. This is a classical way of doing metallic powders for powder metallurgy. Means we use the aluminum powder just to compare these kinetics with the kinetics of the mixture, which was interesting for us. This was the mixture of magnesium oxide in solidified matrix of aluminum, you know. So.
Thank you.
Thank you.